Welcome back. So let me summarize where we are at this point in solving linear equations with linear algebraic pictures. We started way back when with simple linear system of linear equations. So I've got x and y are the unknowns. It's linear because I'm simply adding them and scalar multiplying them by a, b, c, d, and of course e and f are just scalar values. We went through the algebraic picture, we went through the geometric picture, and we went through the linear algebraic picture, which is where we've now landed. And the linear algebraic picture, we rewrote this system of linear equations in matrix vector form. And again, if we do this matrix multiplication, a times x plus b times y is equal to e. That is the first equation. C times x plus d times y is equal to f. That is the second equation. So these are exactly the same. I've just sort of reformulated them. Why? Why did I reformulate them then? Because now solving these, you're going to see, is going to be particularly clean, because once I get a square matrix here, 2 equations, 2 unknowns, 3 equations, 3 unknowns, 4 equations, 4 unknowns, all I have to do is compute the matrix inverse. I multiply by that, I get the identity, I isolate the unknowns, and I have an expression to solve. And, as you're going to see right now, one of the nice things about this linear algebraic picture is we very clearly can now see where there is a unique solution, 0 solutions, or an infinite number of solutions. Okay, so let me just add a little bit of notation on top of this. I have a matrix times a vector is equal to a vector. So there are different conventions in different fields. I like the convention of representing a vector by a lowercase letter with a little arrow above it. Sometimes you will see that bold-faced. I don't like that as much because sometimes it's hard to tell if something is bold-faced. So typically what you will see in this class is a lowercase letter with a little line over it, reminding me that it's a vector and not a scalar. So scalar values, for example, C, B, E, F, D, and A are just lowercase letters, but when we put a line over it, it reminds us that it's a vector. Matrices I typically do as uppercase letters. So here my matrix is M times the vector U for unknown is equal to a vector V. And remember again that the way we solve for this is we left multiplied both sides of the equations by M inverse, which is the matrix M to the superscript -1 for inverse. M inverse times M, of course, is the identity. The identity times anything is that thing. And so we have now isolated our unknown vector U with the components x and y. And now we have an expression. M inverse is 1 over the determinant of this matrix times, and then you manipulate the components of this to get your matrix inverse, and you multiply that by the right-hand side of your system of linear equations, and you have solved the system. Now, the question you, of course, should be asking, here's my solution, U equals M inverse over V. Let me write out the matrix inverse, 1 over the determinant. So again, it's the product of the diagonal minus the product of the off-diagonal. I switch the diagonal elements, and I negate the off-diagonal elements of the original matrix, and this is my 2 by 2 matrix inverse. Now, the question we want to ask ourselves is, when will that exist? Will it always exist? Is it unique? Well, so let's go ahead and look at it. So it doesn't seem like there's much trouble here in the matrix. I'm just flipping around some values. But here, it looks like we should probably be a little bit careful because I've 1 over the product. And so what happens if that product is 0? Well, I have a problem. I can't divide by 0. So we immediately see where we are going to run into trouble. If the determinant of the matrix M is equal to 0, then this matrix inverse does not exist. Okay, well that's nice. It's a nice algorithm. It's a nice way of figuring out if my matrix inverse will exist or not. But what does it mean? What does it mean in terms of the linear system? So let's look into that a little bit, because I think we'll get a little bit of insight into what it means when the determinant is 0. So remember again, my matrix is A, B, C, D. The determinant is the product of the diagonal minus the product of the off diagonal. If that is equal to 0, we cannot invert our matrix because we're dividing by the reciprocal of the determinant. All right, well, let's agree that if AD minus BC is equal to 0, then that simply means that AD is equal to BC. And let me just rewrite that slightly as the same being as A over C is equal to B over D. So I'm going to bring the C over here, and I'm going to bring the D over here. It's not obvious why I did this, but you'll see in a minute why I've rewritten it like this. So again, the determinant of the matrix, we have to multiply by the reciprocal. If that's equal to 0, then we can agree that it must mean that there is a relationship between A and C, the ratio of A and C, is equal to the ratio of b and d, which of course are just the coefficients on the original linear system. All right, so what does that mean? Well, let's go back to our original system. So again, this is the constraint that will hold true if the determinant is 0. This is the system of linear equations. Ax plus by is equal to e, cx plus dy is equal to f. And we can see is if the ratio of these two is equal to the ratio of these two, matrix is not invertible. Well, let's see what that actually means in terms of the equations. All right, let me take this equation, ax plus by is equal to e, and divide by by the ratio of a over c here, and here I'm going to divide by the ratio of b over d. I'm allowed to do that because these are equal. So I'm allowed to multiply every one of these by the same things. I've just decided to divide this by b over d, and you can see why, because that has a b here, this has an a over here, and it turns out it won't really matter what I do over there. All right, so what happens when I do that? Well, let's see. Ax over a divided by c. So the a's cancel, and this is the reciprocal of c, so it comes up top. by over b over d, the b's cancel, this is the reciprocal, the d comes up top. And what do I have here? Well, let me just bring up the c up top. So I have c times e divided by a. So this equation, when this constraint holds, which is when the matrix is not invertible, reduces to this. Well, let's look at that. So now I've got my second equation here, cx plus dy is equal to f, and I have my first equation here, which I've rewritten as, oh, interesting, cx plus dy is equal to ce over a. So when the determinant is equal to 0, these equations look awfully similar, and that should not at all be surprising. Because again, what does it mean when there's no solution or an infinite number solution? Is something is degenerate in the linear system, and here you can see what the problem is. And to really make this explicit, let me rewrite both of these equations in terms of slope-intercept notation. So I'm going to take that equation and I'm going to solve for y. So I'm going to bring the cx over to here, so it's going to be minus cx plus f, and I'm going to divide by d. So over here I get minus c over d, and here I get f over d. And if I'm moving a little fast in the algebra, just go ahead and pause the video and just do the algebra yourself. Now here I'm going to do the same thing. I'm going to solve for y. So I'm going to bring the cx over, so that's minus cx. I've got the constant term here, and then I'm going to divide by d. So I get a minus c over d here, and I get ce over a divided by d. So why did I do this? Well, because this is now in terms of slope-intercept notation. So this is the slope of the two lines, and these are the intercepts. And now what you notice is that my two lines, remember these are two original equations that I've just rewritten according to the case when the determinant is equal to 0. So now you can see that the two lines that these two equations correspond to have the same slope, and they have maybe the same, maybe different intercepts depending on what the values of f and d and c and e and a are. All right, so let's go ahead and draw that. So if I have two lines that have the same slope, they are going to be parallel. Yeah. Now, if these two things are different, if this intercept is different than this intercept, well then they're offset from each other, right? Because that's the y-intercept right there, that's the y-intercept right there. And in this case, there's no solution. We know that. Why? Because if you remember from the geometric picture that what we are looking for is an intersection of the lines. But if the slopes are the same, which is what happens when the determinant is 0, well, there's no solution. And if, in fact, this constant is equal to this constant because of whatever the values of a, b, c, e, a, and d, and f are, well, then that means we have two lines with the same slope and the same intercept, which means that they're on top of each other, which means there's an infinite number of solutions. Any point along here will satisfy both of those equations. So you can see very nicely that once we see that the determinant of 0 is degenerate, we propagate that through the equations, and we see that it exactly corresponds to what you expect, which is parallel lines with different intercepts, or parallel lines with the same intercept, in which case you have no solution or an infinite number of solutions. Now, we can also see this in the vector picture as well, and I like this one a lot, so let me just go ahead and do that. So again, here are my two linear equations that have been rewritten according to the condition when the determinant is equal to 0. So you can see that the equations are basically the same, and that this constant may or may not be different depending on the relationship between a, c, and e, and f. So let's go ahead and look at the vector picture of this. So let me first take these two equations and rewrite them with our vector picture. So I've got the same constant c and c multiplying the unknown x, That's that right there. I've got the same constant d and d multiplying the unknown y. And on the right-hand side, I have f, and then I have ce over a. And again, remember what the vector picture is asking. Find me a value x such that when I multiply it by the vector cc and then add it to a scaled version of dd by the other unknown y, I get that vector f ce over a. Well, let's think about, so remember that what that picture is, I've got these two vectors. I'm going to scale them so that when I sum them, they sum to some other vector. So let's draw cc and dd onto our two-dimensional space here. Well, cc means that the x and the y components are the same, and dd means the x and the y components are the same. So of course these two vectors lie along a unit slope line. Okay. Well, what does that mean? Well, if I scale cc, it's going to move up and down this line. Yeah, of course. And if I scale dd, it can only move up and along this line. So both of those vectors, no matter how I scale them, all they can do is live along this line. Okay, well, if I take two vectors that lie along the line and I add them, what am I going to get? Well, it's got to be a vector along the same line. You can see that in two ways. The head-to-tail construction, or you can see that any sum of these things is going to be, say, just we sum them up, c plus d, c plus d. It's going to be along the same line. So if I have two vectors that lie along a line, all I can get is to a vector along the line. So can I get to that vector right there? Well, I don't know. It depends. If that vector is somewhere out here, well, then there's no way of scaling those two vectors and getting outside of this linear space that I live in. And that's the case when there's no solution. That's the equivalent of two parallel lines when f over c, a over d is not a linear combination of those two things. And if it happens to be that it lies along the line, well, then I have an infinite number of solutions. Well, why? Well, I can multiply cc by some factor to get to here and then don't use any of dd. Or I can multiply dd to get up to here and use none of cc, or any combination of the two. So I can get to that vector by scaling cc and dd by any amount, varying amounts, such that I get to that length, and that, of course, corresponds to an infinite solution. So now you can see that that determinant tells you everything you want to know. If the determinant is non-zero, the solution is unique because there's a single matrix inverse, and we multiply that by the right-hand side of the system, and we have an answer. If the determinant is zero, one of two things is going to happen. There will be no solutions, or there will be an infinite number of solutions, depending on the relationship between the coefficients in the linear system. Okay, good. So we're going to do a little bit more practice, and then we're going to do a little bit of examples of using this type of estimation to solve some interesting problems. And then from then, what we're going to carry on after that is we're going to start asking the question of what happens if we have more constraints than we have more unknowns? What if we have less constraints than we have unknowns? And start to get into some real-world data analytics. All right, we'll pick it up in a few minutes.